Imagine a world without refrigeration. No fresh produce, no cold drinks, and worst of all, no ice cream. Sounds scary, right? But have you ever wondered how your refrigerator actually keeps things cool? As it turns out, there's some fascinating science behind it. In this video, we'll explore how scientists and engineers design and optimize refrigerants to make refrigerators more efficient. Engineers utilize a process known as the refrigeration cycle, a system that effectively transfers heat by circulating refrigerant through various stages of pressure and temperature changes. The cycle starts as refrigerant enters the evaporator as a low-pressure, liquid-vapor mixture. Within the evaporator, the refrigerant absorbs heat from its surroundings, in this case, the refrigerator compartment. This absorption of heat causes the refrigerant to evaporate completely, transforming it into a low-pressure vapor. This low-pressure vapor is then drawn into the compressor. The compressor's role is to increase the pressure of the refrigerant, which simultaneously raises its temperature, converting it into a hot, high-pressure vapor. This pressure increase costs energy, which is typically why the compressor is the component with the highest power consumption in the refrigerator. The constant hum of the refrigerator is actually the compressor quietly working away. Next, the hot, high-pressure vapor flows into the condenser. The condenser provides a large surface area to facilitate heat transfer. Here, the refrigerant releases the heat it absorbed earlier to the surrounding environment, cooling down in the process. This causes the refrigerant to condense into a high-pressure liquid. Actually, if you go to the back of your fridge right now, the condenser is typically located at the back of the refrigerator, and this back area is usually very warm. The high-pressure liquid refrigerant then passes through the expansion or throttle valve. As it moves through this valve, the sudden drop in pressure causes some of the liquid to flash into vapor. This phase change results in a low-pressure, low-temperature mixture of liquid and vapor, which is critical for the next stage of heat absorption. This cooled mixture re-enters the evaporator, where it absorbs heat from the refrigerator compartment again, completing the cycle. By continuously repeating these steps, the refrigeration cycle efficiently maintains the desired low temperature in the refrigerator compartment, while transferring heat to the external environment. From the refrigeration cycle, we can identify several key properties that make a good refrigerant. First, the refrigerant should have a high heat of vaporization. This property allows the refrigerant to absorb more heat during the evaporator phase. By maximizing heat absorption, we can decrease the minimum required circulation rate, which in turn reduces pumping costs and improves efficiency. Second, the liquid heat capacity of the refrigerant should be as low as possible. A lower liquid heat capacity makes the refrigerant easier to subcool, that is, to lower its temperature in the condenser phase. Subcooling ensures that only liquid enters the evaporator, which increases the cooling capacity. This is because liquid refrigerants are more effective at absorbing heat compared to vapor. Finally, there are several trade-offs to consider when selecting an optimal refrigerant involving thermodynamic, chemical, and process safety factors. Key priorities include maximizing heat transfer properties, ensuring the refrigerant is safe to use, and making sure it is compatible with the materials and components of the refrigeration system. Let's explore how to determine an optimal set of refrigerant molecules using a common set of functional groups. For simplicity, we'll assume that the thermodynamic properties of the molecule are the sum of the contributions from its functional groups. Take the common refrigerant molecule R22 as an example. By breaking it down into its functional groups, we find that it is composed of 2 fluorine groups, 1 chlorine group, and 1 methyl or CH group. Each of these groups have a specific contribution to the molecule's thermodynamic property, like heat of vaporization. Let's look closely at how this is specifically done. Here is tabulated data for functional group contributions to thermodynamic properties and derived semi-empirical relations. For example, we can predict the boiling point of a molecule with this equation, where Ni is the functional group and Tbi is the numerical contribution of the functional group to boiling point. This is summed for all functional groups to get the boiling point of the whole molecule. With the group contribution model, we can mathematically formulate an optimization problem to determine which set of functional groups will lead to the best performing refrigerant molecule. Our goal is to maximize the refrigeration cycle efficiency, which we said earlier is done by maximizing heat of vaporization and minimizing liquid heat capacity, as shown by the following objective function. Second, we need to add constraints. The evaporator pressure should be above atmospheric pressure, or about 1 bar, so that there is no leaks into the compressor. The condenser pressure should not exceed the maximum allowable working pressure, which is around 10 bar for most industrial refrigerant systems. To ensure the final molecule is physically relevant, we should also add molecular constraints, given by 3 rules. First, the molecule should contain at least 2 functional groups. A 1 functional group molecule simply does not exist. Second, the molecule should satisfy the octet rule, a common chemical principle which states that atoms bond in ways that allow them to fill their outer shell of electrons. This is the most stable form of a molecule, known as the noble gas configuration. Third, there should only be 1 bond between adjacent functional groups. It wouldn't make physical sense for functional groups to have multiple bonds between them, as this would violate rule number 2. From this program formulation, we need to calculate 4 values: heat of vaporization, liquid heat capacity, and evaporator and condenser pressures. Note how these are not given in the table, because we need to use the relations between the tabulated values to calculate our desired values. Because we are choosing whether to use a particular functional group or not, and the relationships between the variables are nonlinear, this is a mixed integer nonlinear program. I use Excel Solver's large-scale generalized reduced gradient to converge to a solution. This is performed for 3 sets of starting conditions to try and validate the solution's robustness. In all cases, we find that the solution converges on functional groups double bond to oxygen and double bond to nitrogen and single bond to hydrogen, which correspond to the molecule HNO, or nitroxyl. Nitroxyl is not currently a commercially available refrigerant because it's highly reactive, unstable, and difficult to store. Despite this, the molecule is very similar to those predicted by other models. Sehindis et al. Create a model which predicts FNO as the best refrigerant. It's likely that a local minima was reached, as not enough initial conditions and iterations were done to sufficiently sample the highly non-convex solution space. This can be combated by experimenting with global optimizers. There are several other areas for improvement. The Joback and Reed group contribution method is not very accurate, as limited data was used to develop the model. For example, the average absolute error of heat of formation of enthalpy is 15.2%. There are more complex models, like that developed by Nano et al., which account for second-order interactions, how functional groups are positioned relative to each other. These give more accurate thermodynamic predictions. We could also tune the constraints like refrigeration cycle process conditions, or heuristically remove infeasible molecules from the solution space. I would love to explore molecular trends and their effects on refrigerant properties. For example, are there periodic trends corresponding to molecular properties? What is the impact of molecular size? How can we use this data to discover new, efficient, and safe refrigerants? These are open research problems that can be expanded upon by using this foundational model. The optimization was performed with the free Excel add-in solver. The paper, which explains all of the numerical methods used, is in the description below. I've also attached the code and Excel sheet on GitHub. Please make sure to like, share, and subscribe to keep updated, as I have a lot of videos planned on quantum mechanics, fluid dynamics, and machine learning, which I plan to make shortly. As always, thank you for watching.